Wan Shang Hao means good evening in Chinese. This is Mr. Bagaski. This will be lesson 4.4, equidistant theorem. I'd like to give a shout out to Nina Beltrano. So here's our lesson. Let's do it. We're going to start with the definition of what a perpendicular bisector of a segment is. It is a line is a perpendicular bisector of a segment if and only if, how do we write that? Yep, IFF. It is perpendicular to the segment and bisects the segment. So in other words, if we had a picture, let's quickly draw something. We got AB here. Say this line L intersects at C here. If L is the perpendicular bisector of AB, what happens is L is perpendicular to AB, and AC would be congruent to CB, because it's also bisecting the segment that it's going through. Okay, so it's basically taking two ideas and putting them into one. I've warned you once before, but I warn you again that 4.4 is the lesson that is the most challenging. Like in 2.4, when we did the supplements of congruent angles are congruent, and we don't like using that one. And 3.7, when we tried to learn if sides and angles or if angles and sides. Now this one is the idea of equidistant creating a perpendicular bisector, or perpendicular bisector creating equidistant. So the theorem that we're learning is if 2 points are equidistant from the endpoints of a segment, then the 2 points determine a perpendicular bisector of that segment. So we're going to create that something as a perpendicular bisector. We're going to do it the long way, because if you do forget this rule, you can do it by doing a detour proof and you'll be fine. So here's the picture here. You might need to add a couple things to yours to match it, so please do so right now. Otherwise, let's mark our picture up. We have AC congruent to CB. We have AW congruent to WB. And we're trying to prove that this is a perpendicular bisector. So 4.3 is going to come into play with if we could make angles congruent, then we could get something to be a perpendicular. The bisector part, we just need two segments being congruent. So as of right now, what can we do? We can prove triangle ACW over here is congruent to BCW, because you have side, side, and then what's special about CW? It is reflexive. So we'll start there with the two givens. AW is congruent to WB. And then we use reason 1 with his reflexive. CW is congruent to CW. We just proved reason 2, triangle ACW congruent to triangle BCW by side, side, side. Obviously next CPCTC comes next. This is where I have 1 and 2 marked, so I'll take these two because then I can prove these two lower triangles. There's many things you can take, but for me, I am honing in on the bottom two triangles of ADW and BDW. So I'm going to take angles 1 and 2, which helps me prove these two now, because if I bring back AW is congruent to WB, and the reflexive piece down the middle here again, so reason 1 again, WD is congruent to WD. Ta-da! We just proved up to reason 4 triangle ADW congruent to triangle BDW. So now these two triangles are congruent. Our whole goal is to get this perpendicular bisector. So we're trying to create perpendicular and a bisector. So next is obviously CPCTC. So what are we going to do? We're going to take AD is congruent to BD, because there is your bisector part. So this is the bisector part. We also can take from CPCTC angle 3 congruent to angle 4. Ran out of room. But wait a second. If 3 is congruent to 4, I can also say that AB is perpendicular to CW. And then now, that's what reason 5. And then now we can say that, last but not least, CW is a perpendicular bisector of AB. Right on. So what do we have here? Reason 1 is reflexive. Reason 2, side, 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 which obviously then next has to be CPCTC. 4, we proved the other 2 triangles, and it can't be the same as side, side, side. So once again, we'll have to have something different, but I see a side angle side. 3, back to there. 5 was that rule. If 2 angles sup and congruent, then the perpendicular. And 6 would be definition of perpendicular bisector. Not too bad, but I would never do my proof this way. If I know I'm going to have basically like a quadrilateral shape and 2 sides are congruent and another 2 sides are congruent, I'm going to use the equidistant theorem, which I will show you in the later examples that we would do. But now you can see where this idea of perpendicular bisector comes from in this example here. Theorem can go the opposite way, so the converse. If a point is on a perpendicular bisector of a segment, then is equidistant from the endpoints of that segment. Okay, so M is perpendicular bisector of AB, so that means it's causing perpendicular, and it's causing these pieces to be congruent. We're trying to prove that AC is going to be congruent to BC. So this line would be congruent to this line here. Okay. Well, ultimately, what are we starting with? We're starting with that M is the perpendicular bisector to AB. Okay. Well, I told you that causes what from above? Perpendicular, right? And it being bisected. So we can say that CE is perpendicular to AB. Okay. Which is then going to cause us to get angle 1 is a right angle, and angle 2 is a right angle. And then we'll know that angle 1 is congruent to angle 2. We also know from this guy here, AE is congruent to EB. And from the diagram, that's the reason 4, CE is congruent to CE, because what do you notice? This side ends up being reflexive. So what do we get? We get side, angle, side here to be able to prove what we're calling is the 2 triangles of ACE, ACE, congruent to BCE, which then we can end with our favorite step of CPCTC of saying AC is congruent to CB. Reason 1 would be definition of perpendicular bisector. Reason 2, definition of perpendicular. 3, all righty angles are congruent. 4, or reflexive property. 5. We have a side angle side, and we're finishing it up with our friend the CPCTC. Once again, this is the long way to be able to do this proof. I wouldn't do it that way. Here's how I would do it, and here's how I would proceed on doing the homework assignment. That's going to go along with 4.4, which is on page 180. Nope, 187. Yep, page 187. So let's see here. First off, we know C is the center of a circle, and we know D is the center of a circle. So everything is nicely drawn in for us. We don't even have to draw anything in. Center of the circle, so that means C causes radii here and here. D causes radii here and here to be congruent. This is what I'm telling you. If you notice this shape, you notice that it's a quadrilateral, and you have two sides equal distant and another two sides equal distant, then you're going to be able to use the theorem that we learned up above. Okay, so real simple. Reason 1, we said CA was congruent to CB. Same reason, AD is congruent to DB. That means this point and this point are on this line. AB and B are on this line. So what's happening is that A and B are away from each other. So these are the stationary points. So now we end up having this idea of perpendicular bisector. So we can bracket these two, use our new theorem, and say CD is a perpendicular bisector of AB, which then gives us, by definition, AB would be perpendicular to CD. Reason 1, we all know, is all radii congruent. Dos would be, here's the new theorem. What did we have? This idea over here is we're creating 2 points being equal distant. If you don't want to write it out, that's the shorthand. Equal sign and then the word distant. If 2 points are equal distant, then you create a perpendicular bisector. That's what, if I scroll up here, what this theorem says. If 2 points are equal distant, then you create this perpendicular bisector. So that's what we're using instead of doing it as a detour proof and proving the top triangle and then the bottom triangle and doing the whole thing like we did up in that example. And then we can use the definition of perpendicular bisector, because we only want the perpendicular part, not the bisector. It's tough. But my best advice to you is you're going to use this theorem when you notice. Let's go again with example 2 here. AB is congruent to AD. BC is congruent to DC over here. So if that's what we're doing, I notice that quadrilateral shape. These two sides are congruent. These two sides are congruent. I don't want to do it as a detour. Let's use the equal distant idea from it. Okay? Because this line right here, this point and this point are the equal distant points away from each other. They're the stationary points. They're not going to move. Anything on this line then we'll be able to do there, because you want to prove that line BE here is going to be congruent to line DE there, which should be drawn in for you already. So if they're not there, please do draw them in. We're not going to draw them in before the proof. They are here. They're supposed to be there. So what do we have? We have AB being congruent to AD. We have BC being congruent to DC. Told you you're going to use this theorem because you notice the quadrilateral with the two sides and the two sides congruent. We can bracket this together, and reason 1, we can say that AC is doing the perpendicular bisector to BD. BD are the two stationary points. They're the ones between the two non-congruent sides. If we have a perpendicular bisector, using the opposite way, we can then say points are equal distant from it. So now we're going to change and we're going to use this one right here. This is the second part. The second part says if you have the perpendicular bisector, then other points are equidistant. So what's happening is you're using both theorems in one. Reason one, we said if 2 points equidist, then perpendicular bisector. And reason two was, hey, if perpendicular bisector, 2 points are equidistant. In shorthand, it's the hardest one to understand, but it's very, very powerful of a conceptual idea here. So what we're saying is this distance here and this distance here are the same because this point and this point are stationary. They're the points that are being bisected. Okay, so they have to be there. So anything that goes from these 2 points to the line that's doing the perpendicular bisector will be congruent. So if I picked any point, if I said this point right here, these 2 sides of here and here would be congruent. If I put a point here, called it F, if I connected a line from D to F and from B to F, those 2 will end up being congruent. So anything that ends up being from the stationary points to the perpendicular bisector are going to be congruent using this theorem. All right. Good luck to you on this assignment, and we will see you in class. Good night.